Welcome to a course on complex analysis. In this lecture, we are going to talk about a very important topic in the course of complex analysis. This was due to two mathematicians, namely Cauchy and Riemann. These two have contributed a lot, and the equation is named after them, that is Cauchy Riemann equations. That is what we are going to see in this lecture. Let us explore them. The topic that we are going to see, as already said by me, is Cauchy Riemann equations. So let me give you an workings. Actually, let me give you the mathematical workings to derive these equations. Okay, so we know that f of z shall be written as u of xy plus iota times of v of xy. Let us mark this as equation 1. Okay, uh, the partial derivatives of these two functions, that is u and v, must satisfy at a point where the derivative exists. Okay, like the function may not be differentiable at some points, but partial derivatives exist at that point. But if the function is differentiable at some point, then that can be related with the partial derivatives at that point itself. Okay, so let us start by writing z naught as x naught plus iota times of y naught, and del z as del x plus iota times of del y, and we shall write del w as f of z naught plus delta z minus f of z naught. So this is nothing but u of x naught plus delta x comma y naught plus delta y minus u of x naught y naught. Okay, this is going to be the real part. Actually, let me write completely. Okay, so this one plus iota times of v of x naught plus delta x comma y naught plus delta y minus u of x naught y naught plus iota times of v of x naught y naught. Okay, and if you combine real part and imaginary parts together, then you are going to have the quantity that I am writing now. Okay, this one plus iota times of the quantity in v. So this is what we would get. Okay, so let this be there as it is. Now let us assume uh, f prime evaluated at z naught, that is del z limit del z approaches to 0, del w upon del z exist. Then we shall write f prime evaluated at z naught as limit delta x delta y approaches 0 0, real part of delta w upon delta z plus iota times of limit delta x comma delta y approaches to 0 0, imaginary part of delta w upon delta z. Okay, this one we shall write. So let us have this as equation 2 and this as equation 3. Okay, we know this limit exists means it has to be a complex number. If it has to be a complex number, then it can be written in real part plus imaginary either times of imaginary part. Now we will have to understand a physical representation of or physical significance of the partial derivatives with respect to x and y. Okay, this means Derivative means rate of change. Okay, rate of change in x direction. So that is what we say del upon del x. That is the partial derivative with respect to x. Similarly, this is rate of change in y direction. Okay. Now proceeding further. Now it is important to keep in mind the expression 3 is valid as delta x delta y approaches to 0 0. Okay. Now we choose like yeah, okay, we choose delta x delta y approaches 0 0 horizontally. So if it approaches 0 0 horizontally means through what points? Horizontally through the points delta x comma 0. Okay. So here what happens? Your delta y is trivially 0. Hence your delta z is going to be simply delta x. Right? Delta x plus iota times of delta y, which is delta x plus iota times of 0, and that gives you simply delta x. Okay. Now we shall write now we shall consider delta w upon delta z, this quantity as u of x naught plus delta x comma y naught plus delta y minus u of x naught y naught upon what is delta z, that is delta x, plus iota times of v of x naught plus delta x comma y naught plus delta y minus v of x naught comma y naught upon delta x. Okay. Thus your limit delta x comma delta y approaches 0 0 to the real part of delta w upon delta z. This happens to be simply limit delta x approaches to 0. Okay, since delta y is trivially 0. Okay, if you plug in your delta y value to be trivially 0 in this real part, you are going to have u of x naught plus delta x comma y naught minus u of x naught y naught upon delta x. So this is what you have. So from this, what is it? It is simply the partial derivative of u with respect to x evaluated at the point x naught y naught, and this shall also be written as ux evaluated at the point x naught y naught. And now limit delta x delta y approaches to 0 0 to the function imaginary part of delta w upon delta z. This is limit delta x approaches 0, v of x naught plus delta x comma y naught minus v of x naught y naught upon delta x. So this is by the definition of a partial derivative with respect to x. This is delta v upon delta x evaluated at the point x naught y naught, and this shall also be written as vx x naught y naught. Okay, so here hope you people understand the notations, that is ux of x naught y naught and vx of x naught y naught represents the partial derivatives of u and v with respect to x that are evaluated at the point x naught y naught. Okay, now if you substitute these expressions into 3, uh, hence by equation 3 what we get is f prime evaluated at z naught shall be written as ux x naught y naught plus iota times of Vx x naught y naught. Let me mark this as equation 4. Okay, now what we have done is that we have seen the change horizontally. Now we are about to see the change vertically. Okay, how to do it? Let us see. So if we make delta z goes to 0 plus iota times of 0 vertically, that is through the points what 0 comma delta y. Then what is our delta z? It is delta x plus iota times of delta y, and that happens to be 0 plus iota times of delta y, and that is simply iota times of delta y. Okay, therefore our delta w upon delta z shall be written as u of, here what, x delta x is 0, right? So it is x naught comma y naught plus delta y minus u of x naught y naught upon iota times of delta y plus iota times of v of x naught comma y naught plus delta y minus u of x naught y naught upon iota times of delta y. Okay, so we usually do not have the iota on the denominator, so we just multiply and divide it, like we just multiply it, so multiply by its conjugate, so we get minus iota times of, yeah, I suppose minus iota times of u of x naught comma y naught plus delta y minus u of x naught y naught upon delta y. Here the iota and iota gets cancelled, so v of x naught comma y naught plus delta y minus u of x naught y naught upon delta y. Okay, now let us see. So evidently we get limit delta x delta y approaches to 0 0 to real part of delta w upon delta z as limit delta y approaches 0. Okay, real part, so this is the real part here. Okay, this part is the real part, the second one is the real part here. So v of x naught comma y naught plus delta y minus u of x naught comma y naught upon delta y, and this happens to be what, sorry, I wrote it u, it has to be v, right? Yeah, it is v. So it is v, with respect to y we are differentiating vy. This shall be written as del v upon del y evaluated at the point x naught y naught. This shall also be written as vy x naught y naught. Okay, and similarly limit delta x comma delta y approaches to 0 0 to the imaginary part of delta w upon delta z, that happens to be limit delta y approaches 0 minus times of u of x naught comma y naught plus delta y minus u of x naught y naught upon delta y. This is minus del u upon del y evaluated at the point x naught y naught. This shall also be written as minus uy of x naught y naught. So again, by equation 3 we write f prime evaluated at z naught shall be written as vy x naught y naught minus iota times of uy x naught y naught. Okay, so from here, if you wish to write u term in as the first coordinate, you can take minus iota outside. So this becomes minus iota uy x naught y naught. Then here from plus 1 you have taken minus iota outside. So this is going to be simply plus iota times of vy x naught y naught. Okay, let us mark this as equation 5. So if you recall your equation for that as f prime evaluated at z naught as ux plus iota times of vx, and the same thing shall also be written as vy minus iota times of uy. Okay, so from these two equations we infer one condition. Okay, that is the necessary condition for the existence of f prime of z naught. Okay, so that is the necessary condition for the existence of f prime evaluated at z naught. So that is your ux x naught y naught has to be same as that of vy x naught y naught, and uy x naught y naught has to be same as that of minus vx x naught y naught. These two are the conditions. So these equations we name it as equation 6, and this equation 6 is called as the Cauchy Riemann equations. Okay, so let me write that too. So these are also like, so I'm not writing this in brackets. Equations 6 are called Cauchy Riemann. So it is abbreviated as CR equations. So this was named in honor of the French mathematician A.L. Cauchy, who actually discovered and used them, and in the honor of German mathematician. So see, a French mathematician and a German mathematician have contributed these things. Okay, the German mathematician G.F.B. Riemann, who made the fundamental in his development of the theory of functions of complex variables. So these things we have done. So till now we have actually proved the necessary condition for the existence of f prime of z naught, and we summarize that as the theorem. Okay, so I'm out of the running number. You just see what the number is. So this is the necessary condition for the existence of the derivative of a function. Okay, we have proved it, but we have not stated what it is. So the statement I am going to give you now: suppose that f of z is u of xy plus iota times of v of xy, and that f prime at z exists at a point z naught equals x naught plus iota times of y naught, then the first order partial derivatives of u and v, okay, both u and v, these two must exist at the point x naught y naught, and they must satisfy the Cauchy Riemann equations, that is ux equals vy and uy equals minus vx. Actually, this must satisfy the Cauchy Riemann equations at the point x naught y naught. Okay. Also, f prime at z naught can be written f prime at z naught as ux plus iota times of vx, where these partial derivatives are to be evaluated at x naught y naught. Okay, so we are saying this is the necessary condition. I have not written it as the necessary condition, but it is the necessary condition that you can see here. So why are we calling it as a necessary condition? Because this is necessary for the existence of the derivative. Okay, I blended something. This is necessary for the existence of the derivative. It means if if your if your function, your complex valued function is differentiable at some point, okay, then the partial derivatives must exist and CR equations must be satisfied. Suppose if you are unable to see what is the derivative, but still you are able to identify the partial derivatives and check for your Cauchy Riemann equation. If your Cauchy Riemann equations does not satisfy, then you can come to a conclusion that the function is not differentiable at the particular point. Okay, if the function is differentiable at that point, then it will satisfy the Cauchy Riemann equation. This does not guarantee you that all those functions which satisfy Cauchy Riemann equations at some point will possess uh, your what to say, your derivative. Okay, existence of the derivative. Okay, now let us see some examples related to it. Mm, okay, let me quickly go through the examples. So we are again starting with f of z equals z squared. So we know this shall be written as x squared minus y squared plus iota times of 2xy. Hence our function u is x squared minus y squared and v is 2xy. So let us find ux and uy. So ux is 2x and uy is minus 2y and vx is 2y and what vy is 2x. We observe that ux is vy and your uy is minus vx for all points in R2. Okay, because we are taking an order per xy in R2, so that is why I have written it as the R2. Okay, and moreover, f prime at z shall be written as 2x plus iota times of 2y, and here you may take 2 as a common quantity, so x plus iota times of y, and that happens to be simply 2z. This is what we actually deduced from the definition of a derivative itself. Okay, we have just verified it with the help of the necessary condition for the differentiability. Next, we are about to see another example. F of z is absolute of z squared. Okay, so this shall also be written as x squared plus y squared. Therefore, our function u is x squared plus y squared and the function v is simply 0. So the partial derivative with respect to x and y to the function v is 0 and ux is 2x and uy is 2y. Okay, here if you wish to check the Cauchy Riemann equations, ux equals vy, this forces 2x is 0. This is possible only when x is 0. Okay, and uy is minus vx, that is 2y is minus 0. This again forces your y has to be equal to 0. Okay, this is what we actually proved, right? So CR equation is satisfied only at x is equal 0 and y is equal 0. So this means only when z is 0 plus iota times of 0, a complex 0, CR equation is satisfied. Also the function is differentiable only at z equals 0. Now let me present you a problem which satisfies CR equation but fails to be differentiable. Consider the function f of z is real part of z whole squared. We know this function is not differentiable. Okay, at any point this function is not differentiable, but still this shall be written as x squared plus iota times of 0. So the function u of xy is x squared and v of xy is 0. So your ux is 2x, your uy is 0, your vx is 0, and your vy is again 0. So here ux and vy has to be same. If it has to be same, then your 2x must be equal to 0. So this happens only at the point 0. Okay, and your uy is same as that of minus cx minus vx everywhere, but still, okay, here CR equation is satisfied at 0 comma y for all y in R, but f of c is not differentiable. Now you may ask me, then what is the use of this theorem? Yes, for which also I have a problem for you people. And I think I should go with the simplest form of CR equations. Okay. Let me give you. F of z is z bar. We know this function is also not differentiable, but still have to go with the help of CR equations. Okay, so this shall be written as x minus iota times of y. So your u of xy is 1, sorry, x, and v of xy is minus y. So your ux is 1 and your uy is 0 and your vx is 0 and your vy is minus 1. Here ux is not equal to vy for any values. So if at least one of the condition is not satisfied, then we come to the conclusion that CR equation is not satisfied. So CR equation is not satisfied. So if CR equation is not satisfied, then we may easily come to the conclusion that this function is not differentiable. Okay, so these two examples have given you an ideology that if CR equation is not satisfied, then the function cannot be differentiable at all. There may be situations where CR equation is satisfied, but still the function is not differentiable. So the existence of the partial derivatives and the verification of CR equations is necessary for the differentiability but not sufficient. So what can be the sufficient condition? That is what we are going to see in the upcoming lecture. Till then, thank you.